The next topic is the behavior of real gases. In this, we will be studying the deviation from the ideal gas behavior. See, what we find is that theoretically all gases follows Boyle's law, Charles' law and Avogadro's law under all conditions of temperature and pressure. The theoretical values are found to be what matching with as per the law. But practically, when we try to find out that whether they follow these laws under all conditions of temperature and pressure, we get what surprised. What we find is that all gases deviates from these laws. In order to check this, we plotted a graph of the pressure volume versus pressure for the different gases. This graph of pressure volume versus pressure graph, if it is for an ideal gas, should be a straight line parallel to the x-axis where we have taken the pressure. But what we find is when it is plotted for the gases like helium, noble gases, hydrogen, it was found to be what going above this ideal behavior. For gases like carbon monoxide, methane, etc., it first goes down and then goes up, but none of these gases was having the graph what coinciding with the ideal gas graph. This shows that the ideal gases are deviating from their behavior. They are not following the gas laws under all conditions of temperature and pressure. In these graphs, we are keeping the temperature constant. These are isotherms. The same thing we can observe also from the same Boyle's laws isotherm, which is called pressure volume graph. If we plot a graph for a gas at a constant temperature between pressure and volume, we get a graph like this. And when it is same theoretical value, this ideal gas is actually its theoretical value. And when its practical value is actually or experimental value is plotted, we also get almost a similar graph. But the two graphs are not coinciding, which again shows they are showing deviation from the usual behavior. This is because that is why we were always wanted to know what is the reason that why these ideal gases are deviating from their usual gas laws behavior. But first thing to notice, then what are ideal gases? Ideal gases, remember, the actual gases, the gases at usual temperature and pressure are called ideal gases, are real gases. They are not ideal gases. So all gases are called real gases. Now we have to see when they will be showing ideal behavior. We call real gases and ideal gases when they are following what? Gas laws. So we have to see when these real gases which we have around us, they will be showing ideal behavior. But for this, first we want to know the reason why these real gases or ideal gases are not showing the ideal behavior. Then after doing the number of studies and giving a deep thought, it was realized that there are certain problems with the kinetic theory of gases postulates. The two problems were, which were mainly figured out, problems were first, that gas molecules have intermolecular forces of attraction, which that theory, kinetic theory of gases, used to believe that these forces are negligible and they used to neglect it. Then the second was that the volume of gas molecules in comparison to the volume of the vessel are not negligible. You cannot neglect the volume of the gas molecules in comparison to the volume of the vessel, specifically when the pressure is high. Now, due to these two main problems, we were getting that deviation from the ideal behavior. Then it was realized when we have accepted these problems, we can make out, since these gas molecules are having intermolecular forces of attraction, the force with which this molecule is supposed to strike the wall of the vessel becomes always less than the expected value. Therefore, the pressure which we measure is called real, and it is always less than what it should be because the other molecules are attracting it from the backside. Now the correction was made, therefore, the first correction was made in the PV is equal to nRT ideal gas equation, that the pressure ideal was taken as P real plus A n square over V square. So in place of this P, which is ideal one, we will take this P real plus P A and A n square over V square, where this A is called van der Waals constant. It's the same constant, actually it is a constant which has been given by this van der Waals, and he was the one who has given these corrections and the corrections in the formula. This A is directly proportional to the intermolecular forces of attraction. So the magnitude of A gives us the magnitude of the intermolecular forces of attraction between the gas molecules. So higher is this value of A, that more polar will be the gas molecules, the stronger the forces of attraction they will be having. Therefore, more easily they will get liquefied. That's the most important thing. So that was the pressure correction which was done in this. Now after doing this pressure correction, the second problem was also incorporated, and the second correction was done like this. The second correction was the volume of the gas molecules was actually considered to be significant, specifically when the pressure is high, and therefore it was taken as that this volume should be equal to V, which we are taking here as the normal one, or we are taking this as P ideal is P real minus NB, where again this B is here is called van der Waals constant, and B, this is signifying the volume occupied by 1 mole gas molecules. And due to these two corrections done, the ideal gas equation becomes P plus A n square over V square, V minus NB is equal to nRT. And this equation we get is called van der Waals equation for real gases. All real gases under all conditions of temperature and pressure follows this equation, where A and B are the van der Waals constant. A signifies the magnitude of intermolecular forces, B signifies the volume occupied by the 1 mole gas molecules, and their values are constant for a gas, which are usually given. This is how you can find out pressure volume relationship.